Hello, this is joint work with Lijie Chen, and Pam Gupta, Mingda Qiao, and Rosong Wang. So we consider the standard stochastic multi-arm bandit setting where we have n bandit arms, and each arm is associated with unknown reward distribution with unknown mean. We call theta I, and each time we can adaptively choose an arm and a sample and get a sample IID from a corresponding distribution. So the day before yesterday, I talked about the best arm identification problem, and also the last talk, where we want to pick the best arm with the largest mean and using as few samples as possible. Also, we can generalize this problem to pick the best K arms. And in this talk, we consider a significant more generalization of the which is called the combinatorial pure exploration problem. So in this problem, we are given a combinatorial constraint F over the feasible subset of all the arms. We can think F as a family of feasible subsets. And our goal is to identify the best feasible subset using as few samples as possible. By best, I mean the largest total mean. So this, of course, generalizes the best K-arm problem where the combinatorial constraint is a simple cardinality constraint. The problem was first started by Chen et al. At NIPS 14. And just give you two examples. For example, suppose we have a graph and we would like to build a minimal spanning tree on this graph. But we don't know the edge cost of each edge. But we can think each edge as an arm, and we can query this edge. And upon each query, we can get a noisy sample from the true cost. And we would like to use as few queries as possible. And we could have more other constraints, like a general matrix constraint, or ST path constraint, or maybe knapsack constraint. Okay, so here is a previous work, previous result by Chen et al. They gave the following upper bound. So first, they define this complexity term called HC, which is summation of delta I to the minus 2. And delta I is called the gap of arm I, which is defined as follows. So if arm I is in the optimal solution, it's defined to be the weight of the optimal solution minus the best solution which doesn't contain I. And if I is not in the optimal solution, this is defined as the difference between the optimal solution and the solution where I must be in a solution, the best solution where I must be in a solution. Okay, so this definition is consistent with the gap defined for the best arm and the best K-arm problem. So they gave the following upper bound. So here this is a complexity term. We ignore this logarithmic term. So the most important term is this width parameter. So the width parameter is a little bit complicated to define, but just to give you some examples, for matrix the width is 2, which is small. But for paths and matchings, width can be as large as linear. And here is our two questions left in this work. So is this complexity term really a lower bound? They call it complexity term, but they didn't show it's a lower bound. Of course, for best arm problem, this is actually a lower bound. There's a formal proof, but for general combinatorial pure exploration, there's no proof. And the other thing is that their upper bound and their lower bound, there's a gap of n square, and can this n square is a large number, can this be improved? So here is our result. So we define a new lower bound. So let's define low C. So C is an instance, and low C as a optimal solution for the following mathematical program, which is actually a convex program. I will come to this program later. And we proved that at low C and log 1 over delta is actually a lower bound of the sample complexity. Okay, and we can also prove that the low C is actually larger than the complexity term defined by Chen et al. Okay, so this shows that Chen et al.'s complexity term is indeed a lower bound. And in some simple cases, actually our bound is can be n times larger than their complexity term, meaning that it's n times better. And we also gave the following upper bound. We gave a sampling algorithm that with the following sample complexity. So this is the lower bound term, which cannot be improved. And ignore this logarithmic term. And the most important term is log f. So f is the number of feasible sets in the combinatorial constraint. So this can be as large as n. So because f can be as large as 2 to the n. So therefore, our upper bound and the lower bound differ by a factor of at most n. So while the previous bound differ by at most n squared. And we also have a worst case lower bound showing this logarithmic log f factor is actually inevitable in worst cases. It's not instance-wise lower bound, but it's worst case lower bound. In some cases, we need this log f. And of course, we define general problem, general combinatorial constraint, which include NP-hard problems. So in general, we cannot hope for polynomial time implementation of our algorithms. But for important polynomial time solvable combinatorial constraint, for example, path matchings, spanning tree, we have polynomial time implementation. Okay, just a little bit about the proof idea. Suppose let's consider any algorithm that succeeds with probability 1 minus delta. And let's denote Ni to be the expected number we sample from arm I. Alpha is just a factor. And we can show that tau I defined to be Ni over alpha is actually a feasible solution of this mathematical program. So here we want to minimize the total number of samples and subject to the following constraint. So roughly each constraint says the following. So here O is the optimal set, A is the alternative non-optimal set, and this is a symmetric difference. This constraint says, so in order to distinguish the optimal set from a suboptimal set, this is the number of constraints have to satisfy this. And this is proved by actually the change of distribution lemma packaged by Gravier and Kaufman. And the rough idea is we are going to create two instances. And in one instance, O is the optimal solution. And in the other instance, A is the optimal solution. Okay? Then what we do is we slightly change the weight in O minus A by a little bit, slightly decrease the weight of the arms in O minus A a little bit, and increase the weight of the arms in A minus O a little bit. And this gives A the optimal solution, and O becomes the suboptimal solution. And then we create two instances, then we can apply this change of distribution lemma. And each alternative instance gave us one inequality here. And we put all this inequality, and we get our lower bound. Okay, so, and for our second result, we proved that this is better than the complexity term defined by Chen et al. Actually, we can show that the complexity term defined by Chen et al. Is the optimal solution for a very closely related mathematical program where we actually just replace this max with the sum. Therefore, their mathematical program is less constraining, therefore gave a worse bound. And in this paper, we also studied a more general problem. In this problem, we consider also n Gaussian arms with unit variance, and we consider n-dimensional Euclidean space. So therefore, each point is an n-dimensional vector, which can represent an n-arm instance where the ith entry is the mean of the ith arm. And we are also given a collection of disjoint regions in this n-dimensional space. And we would like to find out which region contains the mean profile of our instance. So this vector is called the mean profile of our instance. So we would like to see, okay, so which region contains our instance. And we need to take samples, and we want to use as few samples as possible. So this problem actually generalizes most of the pure exploration problem for Gaussian arms. For example, best one arm, combinatorial arms, and also threshold bandit problem, where we want to return all the arms with threshold larger than a given number. And this cannot be captured by the combinatorial pure exploration. We give new lower bound and a new upper bound. The lower bound is also defined by a mathematical program, and the new upper bound is like following. So this part is a lower bound, cannot be improved, and ignore this term. And the most important term is this n to the 3, and this we think is pretty large, and we conjecture actually so n to the n square is necessary. And in the worst case, because right now we have two proofs. One proof that each proof can give you a factor of n, saying that a factor of n is necessary, but the two proofs can be, we don't know how to combine these two proofs to give you n square, and we don't have an upper bound yet. And in general, we think this is, so this line of work is has close connection to multiple hypothesis testing and sequential experimental design, and this large body of literature that follows Chernov's classical paper, and many of these papers gives you asymptotic optimal algorithm, where asymptotic optimal means that it's optimal when this delta goes to infinity. But look at our bound. So actually, this might be the most important term. So if delta doesn't go to infinity, and for the finite delta regime, also called the moderate confidence regime mentioned in the first talk, and this additive term may be more important, and it's worthwhile to study this term, and I think it's an open question in general. Okay, thank you.
So is there a quick question? So thank you again.